Okay, I'm recording. We're starting a new topic today, and this is the topic of momentum. And it turns out that at very advanced levels, like when people are studying elementary particles and doing the math in particle accelerators and things like that, they aren't using Newton's laws all that much. And the reason for that is that for one thing, in particle accelerators, those particles are moving with relativistic velocities. That means close, very close to the speed of light often, and just not going to work all that well. Uh-oh, I seem to have a frozen screen here. I'm going to have to, oh, what is it that I have to do? Change the camera setting. I think it's snapshot, maybe. Nope. Oh, well, anyway, at those particle accelerators, well, I'm trying to track down the right button here. The things that are used tend to be conservation of energy and conservation of momentum. And so that's what people will use under those circumstances. And so unfortunately, right now, I have to somehow, I don't want to have a snapshot on there. Live broadcast. Oh, I had to find out how to do this a while back. And can't remember just how I had to do it. Because right now, I've moved this out of here. Okay, my screen sharing is paused. Not that it was working. Select the camera. Okay. I may have to exit out of this thing and start it over again. So the recording might stop. Not, I don't know. Okay, now you're looking at the messy room I'm in. Oh, well. Okay, let's get back to VZR1. Oh, rats. This means oh, I have to shrink this thing down. Okay, this is going to take some work. Hang on a sec. That's roughly right. Okay, and I'm showing. I think I can restart this thing. Resume sharing. I think we should be recording. I hope. And I don't know how to get rid of that other stuff that's showing up here. It doesn't seem to want to go away. Oh, that wasn't what I wanted to do. All right, we've still got that going on. Oh, wow. Now we have 5 participants watching me agonizing over this junk here. Well, we may have that crud at the bottom, but we'll just put up with it. Anyway, momentum is the topic for today, and momentum is just easily defined. It's equal to, it's a P with an arrow over the top. That means it's going to be a vector. It's equal to mass times velocity. So the momentum of something is its mass times whatever its velocity happens to be, because mass is always positive and it's a scalar. It's not going to change the direction of the velocity. So the momentum always points in the direction of the velocity. So that's part of it. I'm also going to sort of reintroduce Newton's second law, where if we have the net force acting on something, or whatever the sum of the forces acting on something happens to be, it'll equal ma, but a happens to be dv dt. It's the derivative of the velocity with respect to time. So I can replace that with this. And then something you've probably, if you're in first quarter calculus, you may have learned that if you have a constant inside of a derivative multiplying something, it can be pulled outside of the derivative. Well, if you have a constant outside the derivative, you can bring it inside the derivative. And if we do that here, we get d by dt of mv. Well, mv, I just said, was the momentum of something. And why we use the letter P for momentum, I guess it's because M was already being used by mass. So that's just the way it is. Anyway, Newton's second law could also be written as the net force acting on something will be dp dt, the time rate of change of the momentum. And so you can do that, look at Newton's second law this way. Now, looking at it this way, I'm going to monkey around with some stuff. And well, if you're in first quarter calculus, you won't have seen this before, but if you have something that is like a dx and you integrate it between 2 points, x final and or x initial and x final, what you end up with for this little weird symbol here, it's going to give you the change in that quantity that you happen to have there, if all you're integrating is something like dx. Okay, well, I can do something like that with this, and we're going to come up with something new, some other new idea besides momentum here. If I take and multiply out from underneath, or multiply both sides by dt in this case, so on the left side, I would have F net times dt, and on the right side, I'll have dp. This little thing on the left side here, the net force acting over some time dt, is what actually causes a small change in the momentum. dp is considered a tiny change in the momentum. And we happen to call a force that acts for a brief period like that an impulse. And I think I remembered the letter right that your book uses for impulse. We call that quantity J, and J stands for impulse. Here we go again. We've got a letter that isn't related to it, but anyway, it's what produces a change in momentum. Now, we can integrate this thing and this thing using something like that. But what we would end up with is that instead of some little chunk of impulse, excuse me, we'd have some impulse that's produced over some unit of time, maybe over a large unit of time, but it'll end up giving us the change in momentum. Now, this is all really abstract, but I'll try to bring it back to reality here. Let's think about a force that's going to act for some time. And to keep this a little bit simpler, I'm going to go back to just one dimension. So we'll be thinking about that. So let's imagine that we've got time on a vertical axis and force on the vertical axis, and the force would be in newtons or something like that. And let's just start by figuring we have a constant force, and it acts from, say, 0 to t, and we'd get some F delta t here. T is going to be, I don't know why I wrote t twice, measured in seconds. And if we did that operation from 0 to t of the force times dt, what that weird conglomeration of symbols means there is just the area under this curve. And so that would give us a thing that we call an impulse. And that impulse, in this case, could produce the change in momentum of something. So that's what it takes to produce a change in momentum. So in the last unit, we looked at and thought a bit about the integral of force and position. So instead of having time on the horizontal axis, we had position, and we looked at how a force might vary with that. Now we're looking at force times a change in time. And in the last unit, we looked at how the integral, or the area under an F versus X curve, would produce work and produce a change in kinetic energy. Here, we call the quantity that we get out of this thing impulse instead of work, and it produces a change in momentum. So pretty abstract so far, and a little bit untied to reality, but let's just go ahead and figure out a few momentums for different things. And we can start with, say, some of you have taken chemistry and might be able to easily calculate this, but momentum of ... and we'll start with an oxygen molecule. And this would be O2 at 500 meters per second. Okay, the air in a room has oxygen molecules, it has nitrogen molecules, it has water vapor molecules, all kinds of stuff like that. But an oxygen molecule is composed of a bunch of different ways we can do it. If it's typical oxygen, it's oxygen 16, which is a molecule that has or an atom that has 8 protons and 8 neutrons. That's mostly what give it its mass. And if you've had chemistry, you might be able to follow that. But at any rate, if you've got a molecule, you've got 2 of those things. And so you'll have 32, well, you'll have 16 protons and 16 neutrons between those 2 atoms, and that adds up to 32. And the approximate mass of a proton or a neutron, they're pretty close together. It'd be about 1.67. The mass is going to be 1.67 times 10 to the minus 27th kilograms, which isn't much, but we've got 32 of them, so we're going to have a whole bunch. So anyway, we'd have 32 times. Now, this isn't going to be very precise, but it'll be okay for what we're doing here. it's going to have a mass of, I'm just going to round it to two significant figures. I'd say about 5.3 times 10 to the minus 26 kilograms. Now, if you wanted to be more exact about it, you could look at the molar mass of oxygen. You could divide that by Avogadro's number, 6.02 times 10 to the minus 23rd, and then multiply it by 2 because you've got two oxygen atoms, and figure it out that way. But they're going 500 meters per second. So in this case, the momentum is going to be that 5.3 times 10 to the minus 26th kilograms times 500 meters per second. So just multiply the number I just got by 500, and I get not much. 2.7 times 10 to the minus 23rd. Now, the units of momentum are kilogram meters per second, and there's no abbreviation for momentum. We just always call it kilogram meters per second. And so we're not going to invent a new unit for this particular thing. You'll be happy to know. We'll just go with what we've got. So that's on the small end of things. Let's move up a few scales of magnitude and look at a 90-mile-an-hour fastball. What's the momentum of that? Okay, well, 90 miles an hour turns out to be about 40 meters per second. The mass of a baseball is about 0.14, yeah, I'll just call it 0.14 kilograms. 90 mph is about equal to 40 meters per second. And so just the product of those two, the momentum of a baseball, is going to be 0.14 kilograms times 40 meters per second. Might be able to do this in your head, huh? How about 5.6 kilogram meters per second? Could you get that? Maybe. Gonna check it just to make sure. Yep, 5.6. Okay, so that's maybe a little more familiar. How about a world-class sprinter in the 100 meters, and maybe they're going at about 10 meters per second. And I'm just going to make up a number for their mass, maybe 85 kilograms. Okay, so the momentum of that will be, do this in our heads, 85 kilograms times 10 meters per second, that's 850 kilogram meters per second, or 8.5 times 10 to the second. Now that's getting up here where this would be about 3 times 10 to the 25th times bigger than this, so quite a bit more. Now let's just go to a car. 1,200 kilogram car at 30 meters per second. The momentum of that, see if you can do it in your head. This is 3 times 10 to the first. This is 1.2 times 10 to the third. So multiply those two together and you get 3.6 times, oh, now I lost my place. Let's see. 10 to the, 10 to the first, that's 10 to the fourth. Yeah. 10 to the fourth kilogram meters per second. Okay. The book does an example similar to this, and they compare a couple of things like this and make a note of the fact that this is about 10 to the 27th times bigger than that, which is 10 to the 9th is a billion. So this would be a billion, billion, billion times bigger than this. So there are some typical kinds of momentum. And so they can be huge ranges of things. Consider all of them. So let's do some example problems here and maybe talk about some changes in momentum and see how those come about. So this gives us more precision on the mass of the baseball. On a faster pitch, instead of 40 meters per second, it's going 45.0 meters per second. And if the velocity of a pitched baseball has a magnitude of 45 meters per second, and the batted ball's velocity is 55 meters per second in the opposite direction, find the magnitude of the change in momentum of the ball and the impulse applied to it by the bat. Actually, the impulse applied to it by the bat is the change in momentum of the ball. So let's imagine that our change in momentum here, delta P, is going to be P final minus P initial. And I'm going to draw a picture for what's going on here. Let's just suppose that we've got the ball going in this direction to start with. So there's V initial. And then the batted ball gets swatted right back at the pitcher at 55 meters per second. He'd better duck. So V final is in that direction. And let's let positive be to the right. So in fact, we could have this be the x-axis and this could be the y-axis. And we don't have to do anything in the y direction because it's horizontal velocity. Well, mv initial in this case, we can put numbers on it, but it'll just be whatever the magnitude of it happens to be, mv initial in the I hat direction. Okay. mv final is going to be in the minus I hat direction. So minus mv final in the I hat direction. And delta P is P final minus P initial. I can turn this to a scalar equation. It'll be that minus mv final, that's the final momentum, minus the initial momentum, which is mv initial. And what I'm going to end up with is that I'll have the mass times minus V final minus V initial. Let's see, did I get that right? I think I did. V final minus V initial. That should work. So, yeah, I want to be careful with this. Anyway, the delta P will end up equaling the mass, 0.145 kilograms, times V final, since I had put a minus sign out here to indicate its direction already, this will be minus 55 meters per second. And then minus the magnitude of that initial velocity, which was 45.0 meters per second. And I think that's minus 100. So what I'll get here is minus 100 times 0.145, which ends up being minus 14.5 kilogram meters per second. Okay, now what did we have for that baseball in the first place? I had a slower pitch. I had about 5.6 kilogram meters per second, and this was a faster baseball, and it's the change in momentum that got hit back in the opposite direction just as fast or faster than it was going in the first place. So not surprising that that's about 3 times the size. Now, this is the magnitude of the momentum change is just going to be the 14.5 kilogram meters per second. And that's also the impulse applied to the ball by the bat. That's what produced the change in momentum. So new terminology here. However, if the ball remains in contact with the bat for 2.00 ms, so that means milliseconds. Millimeter is 10 to the minus third meters. This would be 10 to the minus third seconds, or 2.00 times 10 to the minus third seconds. Find the magnitude of the average force applied by the bat. Well, here's what we're doing here. We're going to imagine that we have a nice constant force. And actually, in a collision like this, probably what's going to happen is the force is going to start off very small, go up quite a bit larger, and then come back down to zero, something like that. And it's not going to, it'll have a maximum value and small values at the beginning and end of the collision when the baseballs actually get deformed a whole bunch in a collision with a bat. It's kind of interesting. But on average, we can calculate this area right here. The area of the rectangle will approximately equal the area under the curve if I hadn't drawn the curve so tall. But that's all right. We're going to be after that average there. And that impulse is equal to the average force times the time during which this collision between the bat and the baseball happened to occur. So the average force is just going to be, in this case, that J number, the impulse divided by the delta T, and 14.5 kilogram meters per second divided by the time was 2 milliseconds, 2.00 times 10 to the minus third seconds. And you can convince yourself of this. Imagine the second on the bottom is like a second divided by 1. Invert and multiply. And what you'll end up with for units are kilogram meters per second squared. That happens to be a Newton. Okay, well, that's good. That's a force. So 4.5 divided by 2 is going to be 2.25. Wait a minute. It's supposed to be 4. It is 14.5 by golly. Okay. Trying to do stuff in my head. Anyway, 14.5 divided by 2 is going to be 7.25 times 10 to the third, which I could just write as 7250 kilogram meters per second, which is 7250 newtons, which is quite a bit, actually. When somebody swings a bat with full force, it would exert a fairly large force on you for a short time. And that's what it happens to be in this case. Okay, that was quick introducing the idea of impulse and change in momentum. Never even seen it before. One of the interesting places that we study momentum is when weapons are fired, like a rifle is fired. The rifle exerts a force on the bullet, which pushes it out of the barrel. And it's actually exhaust gases and all kinds of stuff. But it turns out the bullet is exerting a backward force on those gases, which then exert a backward force on the rifle and pushes the rifle against the shoulder of the person who's firing the gun. And we call that recoil, but it ends up being conservation of momentum. If the system, the rifle and the bullet, starts off at rest, it has no momentum. If some part of it takes off going in this direction with some momentum, the other part is going to go in the opposite direction with equal momentum. How can that be? Well, here's how it can be. Make a graph of force versus time. And let's suppose that when the weapon is fired through some mechanism, the rifle exerts a force on the bullet. And that force maybe looks like that for a little while. Well, Newton's third law still works in situations like this. It always works. The bullet will exert a force on the rifle that is equal and opposite at every instant. And so this would be the force of the bullet on the rifle. And that force of the rifle on the bullet happens for a very short time, some tiny fraction of a second actually, but at every instant, there's a third law partner of that. That's the force of the bullet back on the rifle. And the two impulses end up being equal and opposite. And so the bullet goes one way with its tiny mass, it goes pretty fast. The rifle recoils the other direction with a much larger mass. It doesn't go nearly as fast, but if you don't have it held tightly to your shoulder, it's going to build up a pretty good speed there and slap into it. And you want to be careful when you're doing stuff like that. So 7-kilogram rifle, 10-gram bullet. Okay, this is 7,000 grams. This is 10 grams. So this thing has 700 times the mass of the bullet. And the bullet travels with a speed of 700 meters per second. What's the speed of recoil of the rifle? Okay, so we can kind of, well, that wasn't one of my better drawings. Anyway, this is going to be an ancient rifle here, like something from the Revolutionary War. Anyway, to begin with, the bullet is inside this thing and not going anywhere. And then the rifle is fired. And afterwards, we have a bullet heading out in this direction. Nice little round piece of shot. Then we'll have the rifle, which I don't want to try to draw something that complicated again. Anyway, I'm going to imagine the rifle is a rectangle instead. It's going to recoil in this direction. So here's the rifle. Here's the bullet. There was no momentum to start with. And so this system, rifle and bullet, will have no momentum afterwards. So whatever momentum the bullet has in that direction will be matched by an equal and opposite momentum in the other direction. That's one of the conservation things about momentum that we'll use. So 10 grams, the momentum of the bullet will equal 10 grams is 0.010 kilograms. And 700 meters per second. We'll have that going on. And then whatever number that ends up being, I think it's 7.0. Check that. 7 times 10 squared. Yeah. Actually, no, times 10 to the anything. It's just 7.0 kilogram meters per second. So that's just the momentum of the bullet. that's going to be the momentum of the rifle as well, but it's going in the opposite direction. But if I just calculate the magnitude of the momentum of the rifle, that will equal the mass of the rifle times speed of the rifle, and 7 kilograms times whatever the speed of the rifle ends up being. But the product of the two, oh, look at that, 7 kilogram meters per second. So anyway, the speed of the rifle will end up being 1 meter per second when I divide both sides by 7 kilograms. Okay, well, that's not very much, but if you happen to be holding the rifle loosely and there's a little bit of a gap between it and your shoulder, it'll sock into it at 1 meter per second and could give you a pretty good bruise. If you hold it tightly to your shoulder, then that 7 kilograms of the rifle gets added to your mass, or your mass gets added to it. And now you'll have a much larger object that's recoiling, but it'll be recoiling at a much lower speed than the rifle itself was. And so that's something that happens. Okay. This is another one. Okay, this one's actually looking at the gases that contribute to the recoil of the rifle. So it's not just the bullet that's going out of there, it's also the gases. I don't have really interesting questions for this section, I guess. Yeah, and then another one with guns. Okay. After this, it's more fun to talk about car collisions than stuff like this sometimes. Expanding gases that leave the muzzle of a rifle also contribute to the recoil. The 30 caliber bullet has a mass of 0.00720 kilograms and a speed of 601 meters per second relative to the muzzle when fired from a rifle that has a mass, this is a less massive rifle, 2.80 kilogram. The loosely held rifle recoils at a speed of 1.85 meters per second relative to the earth. Find the momentum of the propellant gases in a coordinate system attached to the earth as they leave the muzzle of the rifle. Okay, so here's what's going to be going on here. We've got the rifle. We have the bullet that's headed out in this direction, and the rifle is recoiling in this direction. And there was no momentum before the rifle fired the bullet. But if we look at what's going on afterwards here, we'll have some amount of momentum that isn't accounting for something. And we'll find out that it's the cloud of gases that are coming out of here as well. So we want to find the momentum of the propellant gases. So here we'd have a momentum of the gas going presumably in that direction. The bullet's going to have a momentum that's in that direction. The rifle's going to have a momentum in that direction. So it'll have its own momentum, and it's going to be a minus sign. I'm putting an arrow on there, but the momentum of the rifle is actually going to be headed back in that direction. Oh, in fact, yeah, I'll just indicate the direction by the sign on these things. So for the bullet, we'll have .00720. I guess they can measure a speed that precisely. All right, there it is. I don't know where I set down my TI-84 calculator. 4.33. And the units are just multiplying these things together, kilogram meters per second. For the rifle, it's going the other direction. And so I'll take its mass, 2.80 kilograms, times 1.85, but I'm going to put a minus sign on its velocity. And I get minus 5.18 kilogram meters per second. So we've got a situation here where momentum doesn't seem to be conserved, where the rifle going in that direction has more momentum than the bullet going in that direction, and something's missing. And that is that the gas here must have a momentum that's headed to the right as well. And so we have P gas plus P rifle plus P bullet. The momentum of all of those things has to add to zero, but that's not what we have. So we can say that the momentum of the gas is going to equal the negative of the momentum of the rifle minus the momentum of the bullet. And then we'll have end up with 5.18 kilogram meters per second minus the 4.33 kilogram meters per second. That's the momentum of the gas. It's also exiting the barrel of the rifle. All right, then 5.18 minus 4.33. The number doesn't matter. It's just 0.85 kilogram meters per second. But there, you can look at situations, and if you end up with some missing momentum, there must be something that's carrying that momentum away. And in this case, it's the, well, they told us ahead of time, it's the propellant gases that were leaving the barrel as well. Yes, that's kind of it for that one. The conservation, we're going to be studying collisions here shortly, starting to Thursday or Wednesday, I mean. But one thing that happens with collisions, in a collision between two objects, and then I'm going to put a qualifier on this, and before external forces get a chance to provide an impulse to the objects, the momentum before and after the collision will be the same. Where this idea works is if you have a collision, say, between two cars. So one of the cars is going in this direction. This would be M1 and it'll have V1 initial. And let's just suppose that this vehicle happens to collide with another one and hits it sideways like that. So here's M2 and V2 initial is in this direction. And the two vehicles stick together after the collision. So afterward, you've got a severely shortened M1 with a crumpled up part in the front of it. So here's M1, and it's stuck to a pretty well dented M2 here. After the collision, they'd be heading in some direction here, skidding along the ground, and the combined momentum of these two things added as vectors will equal the momentum of the combined masses after the collision. And people who show up at accidents afterwards block off the roadway, go out there with bright lights, measure all kinds of stuff. They can measure skid marks that show where the collision occurred, and they'll see where the thing stopped moving. And by the length of the skid marks, they can determine the initial velocity of the two objects, and that would be the velocity the instant after the collision. And then they can work backwards and use conservation of momentum and figure out how fast the two objects must have been going before the collision. And knowing the masses of the cars ahead of time, they can do conservation of momentum and determine the speed of this car before the collision and this car before the collision. So that's what they do in accident reconstruction. And conservation of momentum is a big deal, or one of the most powerful tools that they have in solving something like that. So who knows, maybe you could get a job working for the state patrol. Although I read a police report where someone was writing about a collision between a couple of motorcycles, and they kept quoting these physics equations according to the law of thus and such a thing. And then they talk about just plugging numbers into the equation. And there didn't seem to be any understanding of the mathematics or the physics involved at all. But they knew how to plug numbers into an equation. And that was about all. So if you've had this class, you might be able to do better than they do. All right. So here we've got another gun problem. A machine gun fires 35-gram bullets at a speed of 750 meters per second. If the gun can fire 200 bullets per minute, what is the average force the shooter must exert to keep the gun from moving? And we're going to consider only the horizontal direction in this case. Well, those 35-gram bullets, 200 of them, are going to be leaving this gun, but that's spread over an entire minute. So we can figure out the combined momentum of these 200 bullets. We can figure out the momentum per bullet and multiply that by 200. And there's got to be that would be an impulse that's given to those bullets, but that impulse is spread over an entire minute. So if we divide by the total impulse by 60 seconds, we should be able to figure out the average force. And so here's what we'll have. The total impulse is going to be some average force times a delta t, and that'll be the total momentum of those bullets. They start off with no momentum, so we can say the P final for the bullets minus P initial for the bullets. And so and P initial for the bullets is 0. So we'll just figure it out. So F average times 60 seconds is going to equal, well, we'll take one of those bullets. 35 grams is 3, actually, yeah, I'll write it as 35.0 times 10 to the minus third kilograms. A gram is 10 to the minus third kilograms, and then multiply by 750.0 meters per second. So 3 sig figs here, 4 on that one, and then 200 of those bullets. And that's just a number of bullets. So that's all I need to worry about on that thing. And the average force, actually, let's go ahead and multiply those two together. And I forgot to put the minus 3 in there. So I would get something like 5.25 times 10 to the third kilogram meters per second. And I'm dividing by 60 seconds. Let's see. And again, think of that as kilogram meters per second divided by seconds over 1. You invert and multiply, and you multiply by 1 over seconds. And so you get kilogram meters per second squared, or newtons. So then I hope I plugged the numbers in there right. I get about 87.5 newtons, which is not a lot, I guess. It'd be around, I don't know, 18 pounds or something like that. I can't remember the conversion. 4.445, maybe. Yeah, I get about 19 or 20 newtons roughly, or pounds, I mean. So anyway, that's the force that you would have to exert to keep the gun from recoiling. So anyway, just using the idea that impulse is equal to an average force times a delta T and equals the change in momentum of those bullets. So a few basic ones. Some of the things that we're going to do in this unit are look at collisions, and there are collisions of various type. One type is called an elastic collision. Elastic collisions are collisions for which kinetic energy is conserved, and you can tell if a collision is inelastic. That's one in which kinetic energy is not conserved. If energy goes to something else, and if you can hear a collision, it takes energy to make sound, and so that is an inelastic collision automatically. Just because it's solid doesn't mean it's not elastic, though, because sometimes whatever forces are going on or doing things aren't necessarily making noise. But in reality, nearly all collisions with which you're familiar are inelastic, that some sort of energy is taken out of the system. Although at school, I've got some magnetic carts where I can do a pretty good job of faking an inelastic collision with those things. About the only place where truly elastic collisions occur, where energy is conserved, is when you're talking about collisions between charged particles at the atomic or subatomic level. And those individual particles just don't have a way to get deformed in a collision or make noise or anything like that. And actually, they don't actually come in contact with each other. It's at that level, it's just electric repulsion that's keeping them from hitting each other, and they'll just bounce off and have elastic collisions. So that's a fun place for energy conservation, and that's what's used. The picture that I have on the home page for our campus course is one of the computer images that are generated at the CERN particle accelerator on the Swiss-French border. And that's where, when they have those collisions going on, they're looking at conservation of momentum and conservation of energy. And that's the way that they analyze those things, using relativistic Einstein's equations for energy and momentum. Turns out they both behave much differently when things are going very close to the speed of light. So, but we won't study relativity until the end of spring quarter. And that's how that stuff will work. Okay, their introduction. I put up a survey and sent out a message. I'll have maybe 1 or 2 review sessions. It looks like having one at 6:30 tonight might work well for one, but if you could attend one earlier in the afternoon, well, not that much earlier in the afternoon. I didn't even start it till 2, but you know, if you might be able to make one at 4 o'clock or something like that instead of an evening one, put a vote in for when you'd like to have one, and I'll be able to look at it and try to accommodate as many students as possible with one or another of a couple of review sessions for the test. And before you come to a review session, take a look at the sample problems that I put up, and also I think I posted an old test as well. Have a look at those things, try to solve some problems, be thinking about stuff so you can come to the review session not being a blank slate and have some idea of the specific questions that you want to ask. So I'm going to stop there and maybe talk to some of you later. Otherwise, see you tomorrow.